Okay, so in this blog, I want to show you guys how I learned Golang and really just how I approach learning any new language. Now, I was going to do one big video where I set up my entire laptop from scratch for Go development work, but the setup part just kind of took too long. It took quite a bit of video time, so I've separated that out into its own video. If you want to see how I set up this environment here, and what I have here is basically my standard Go install. I've got VS Code also configured with all my Go plugins and all that stuff. So if you want to see how I went about setting that up, it's not fairly complicated, simple stuff, just a lot of download and install kind of thing. But I do have a lot of intro, just kind of intro blurb about what I'm doing here and there as well. So feel free to watch that video. If you want to just jump and dive in headfirst into this stuff, then this is probably a good place to start as well. Now, as I stated in that video, what I am going to go through in this video is familiarize us with Golang by implementing a circular doubly linked list, and then using that linked list to build more stuff. Along the way, I'll be unit testing all my code as we go along as well. The idea here is to get to know what a typical development experience on a day-to-day basis feels like with Go. And I do that not just with Go, but some of the other languages that I've learned in the past as well. I do it this way because basic tutorials just don't give me that practical, here's what the day-to-day pragmatic experience is as a developer of this language. So I do something like this to really sink my teeth in. And you'll hopefully you also agree that it really gives you a good idea what the syntax and everything looks like. And how you really use that language. Okay, so let's start implementing a basic list abstraction just to get things started. Before we actually start writing code, this code over here is just some leftover stuff from the setup video I was just referencing. And this kind of gives them some details, just to get our bearings in the language. Right off the bat, you'll probably notice the main function because that's probably the most familiar thing in here. A lot of languages have a main method where the entry point starts. In addition to that, you'll notice that it's in package main, and it has to be package main if you want your main method to be the entry point. That's something that's interesting. Not a lot of languages have that requirement, but if I change this to package local, for example, then this stops being an executable. So I'm in the local package here. I haven't built anything, so if I do a go build, I don't get anything, right? If I do a debug, start debugging, it fails, right? So I basically just change that to main. Do a go build. Now my local, boom. If I come here, I start my debugging. And that succeeds. And in my debug console, I've got my output. Awesome. So, just to get a bearings here, that's what package name looks like. Also, there's some other semantics around packages in Go, which we'll, get to know as we go through this exercise. Kind of like, your folder structure and stuff is pretty important. And that's kind of, Java does the same thing as well. And then finally, I guess the other thing that's kind of sticking out here, two more things. Really, the import statement. This is very, very common. Header files in C, imports in Java. Almost every other language, has some way to kind of reference libraries that you're using. That's really what that is. FMT's got probably like one of the most commonly used libraries or functions in Go. This is where you basically do all your standard I/O stuff, as well as I believe it has also just like string manipulation things and all that stuff in there too. But we'll get very familiar with that in writing any Go code of any importance. And then let's see. And then struct. So Go doesn't do classes. Instead, it does structs. But Go does do OOP. Basically, what you do is you define data fields by themselves in a group in a struct. Structs are different from classes in that they don't have functions, right? Functions are then external to your data. But you can attach functions to specific types, specific structs and stuff to essentially achieve OOP. Now Go does not do inheritance, which we'll see, but that's for later. So that kind of gives us a good idea of what this is over here, right? And then I'm using the person type that I created to do something very, very basic. Okay, so let's get into lists next. Now, before I start worrying about organizing my code properly, I just want to pound out some working code. so that I can start gaining some fluency and intuition in the language. So let's create a very basic list abstraction. We'll have 3 operations, and later on as we evolve this, we'll add a lot more. So I'm just gonna put in some comments here. So for my basic list ops, what I want is an add, and I'm not using Golang syntax here. This is just generic syntax, kind of pseudocode essentially, where my add will take one argument, just some data of any type, and it'll return nothing, right? Just void. Then I'll have a slice, because once I start adding things, I'm gonna be able to tell back from the list, well, how big is the list at this point, at any given point, right? And my size doesn't take anything, no arguments, but it returns a long. Here I'm going to call it long just so that I can have the list grow to be as big as we can possibly represent the size in the types of integer types the language offers. So just the longest possible unsigned integer type you can give me from the language, okay? And then get. So the get will take an index because you're trying to get a specific or data stored at a specific point in the list, and that's going to have to be the same type as whatever your size is, right? Yeah, just so that you can support just as many. And then it returns data, right? Whatever data you've stored at that index. So any type there. Cool. So now that we have our operations to implement, let's talk about state. So once I have my requirements, the next thing I'm thinking about is, well, what state do I need to capture to maintain, capture and maintain to provide that implementation, right? So what is a linked list here? I don't think we have our requirements fully gathered here. Of course, these operations are beginnings of requirement. What are we really building here? We're building a linked list, right? A circular doubly linked list. But what is a linked list specifically in general? So linked list, most of you should probably already know this. It's made up of nodes, right? And each node has some data and then references to its neighbor nodes. And that's the linking part. So let's create a struct. Now I'm going to write actual Go code called a node, right? At least struct. And so what does node have? So first of all, it has data, and we're going to capture any. So any can mean different things, or it can be captured in different types of different languages. So if you're writing Java code, we've called it object, right? A lot of the loosely typed languages, you could have just called it var and be done with it. Go is strictly typed, so we have to assign it some type here. And so we are going to assign it interface, which happens to be the most, it just says it can be anything as far as Go is concerned. That's really how Go captures that. There's a subtle difference here between object from Java and interface, where object is actually a class with methods and some state. Interface is just nothing. It's just type with no other state or operations associated with it, right? And then, okay, so we've got our data. And then what type we're creating here? We're creating a doubly linked list. Now, if we had a single linked list, which is the most basic linked list, which is acyclic singly linked list, well, let's just draw it out real quickly so it's clear in our head, right? So basically, a linked list of any type will typically have a head. That's the head node, right, where we start. That's the beginning of the list. Now, in a acyclic singly linked list, the most basic type, we typically just have a next reference, right? And so we can capture that here. And it's going to be a pointer. Hopefully, you do your Go tutorial, because they cover pointers if you're coming from a language that does not do pointers. So this right here is the next part right here, right? So it contains basically a next reference to its next node, the nearest neighbor. And let's say in this list it's some node, right? N1, whatever, right? And then N1 will have a reference to its next node, which will be N2, and then that will have its N3, and so on until you get to the last node, which is the tail node. And then tail node's next is going to be nil. It's not going to refer to anything because it's the last node in the list. This is an acyclic, singly linked list. There's single link, right? A circular doubly linked list is different. First of all, it also has links going backwards. So the first node in addition to pointing to its next node, it also points back to the previous node, which is the head node, right? And so does this guy, and so does N3, and so does N tail. So they're all pointing back at each other, and so we capture that here as previous. And then the part that we haven't captured here, it'll just kind of become obvious as we implement iteration and stuff later on, is that in the circular doubly linked list, the tail also has references, and it actually then points back to this guy. I'll just do it like this. You get the idea, right? So essentially, these guys point back at each other as well. So, and this is where the circle or the cycle comes into play. So it's a cyclical or circular doubly linked list. There's two links, and the it's circular in nature. The list never ends if you keep iterating on it, or the iteration never ends, I should say. Okay, so armed with that and with our node type, we are ready to go implement the list type, which will make use of nodes. And really, the list type ends up being pretty simple. Most linked lists, and I'll just use simple, maybe capitalize this to stay in true camel case. But I'll talk about casing here in a second, which if you've done the Go tutorial already, like most of us, you know exactly what that is. But yeah, these are not exported here, right? And so the linked list, it really just needs to have a head, which is going to be the node that is the beginning of the list. And then you don't have to do this because you can implement an operation for it, but you can make it a constant type operation if you just hold on to the size at all times as well. And we're not going to do int. We had said we want size to go back to be long. And really what is not captured is an unsigned long, right? Let's call it ulong. And so ulong in link here is going to end up being your uint64. Awesome. Cool, so those are my structs. So then I essentially need to go ahead and implement the operations. And so how do I implement my operations here? So as I was mentioning earlier, Go does not have classes. Instead, it has structs and functions that can be attached to those structs to achieve some sort of object-oriented programming here, right? So whereas in typical OOP language, you would have data fields and functions, you really keep the functions somewhat external, although you'll typically define them in the same file and stuff. But it's not inside the type, it's outside the type. And you attach it to a specific type by doing this little parentheses syntax before you start defining the function. And this thing will be of the type linked list, right? And we do an add. Let's actually go ahead and make linked list. It just seems kind of weird that we have an exportable function, but we don't have an exportable type that's attached to it. Okay, so what are we adding? So we're adding data, as we captured earlier. Interface is that type to represent any type, and it doesn't return. Return anything. So basically, we can do this. Okay, now let's hit save, and so far it compiles, so I like it. So, and let's just call it what it is, right? Oh, yeah, let's leave it alone for now. Let's call it circular doubly linked list. And this is my GoLint kind of complaining to me, saying, hey, you've got an exportable public type, why aren't you writing comments for it? So, and it has a particular syntax about it as well. It said it needs to have a comment, and it needs to start with that type name. So if I did this, it complains. It's saying, hey, comment should be of the form start with the type name first. So I can do this, and it's happy. Well, it's not. It needs more detail. Okay. There's a doubly linked list. It's very self-explanatory, but whatever. Add some new data node to the tail of the list, right? Okay. And of course, I've gotten rid of my linked list now, so let's do this. Okay. All right, so now my lint and my compiler are happy. So we can go ahead and implement the add function. Before I do that, I'll just go ahead and do this for all my other types as well. Okay, so we had size that didn't actually take anything, and instead it returned an unsigned long. Okay, and then we finally had a get that also, well, it did take something. It took the index, which is again outside long, and it returns our data. Now, this is different than a lot of the actual linked list implementations you'll see. I'm not trying to put out a very competing, linked list implementation that's going to replace what's out there. This is just to learn Go, right? A lot of the actual linked list implementations you'll see, I think the Go's standard linked list implementations does this, is where they don't actually return the data, they'll return nodes a lot of times. Reference to the actual node that's capturing the data. And that's because a lot of the algorithms actually work well with linked list when you actually return the node, so you can have more control in your operations where you're using the linked list. We're not going to worry about that here. I'm going to instead opt to create a better, try to create a good encapsulated linked list where the internal details like nodes and other things that we'll see in the implementations are really hidden from the consumer of this type, and instead they just see nice operations and they just get back whatever they provide. They don't worry about a node and links that are captured in there manipulating any internal state. Well, we're going to try and stay away from that. Just to see what good encapsulation looks like in Go. Okay, so now we're ready to start implementing this. So let's implement the easiest operation first, which will be size. It's super easy. Actually, before I do that, let me fix these comments too, because I just copied and pasted them. Okay, so size returns the number of data nodes currently part of the list, right? And get returns data stored in the node specified by the index. And kind of like the understood thing here is in linked list, nodes are going to be present in insertion order, right? And so it's going to be in that order that this gets returned. Okay, why is this complaining? I'm not actually sure. Oh, that's right, because both of these things return stuff, and we haven't returned anything. So size is easy to do. All we have to do is return list.size. Awesome. And we're good there. So now you could say this is too easy, but it could be easier. Why can't the users of this list just look at the variable directly that we're returning? We're not doing much with it, right? Well, that's a good opportunity to talk about state privacy or access control and Go here for a second. So a lot of languages don't provide state access control in their syntax, right? In those languages, you could very well do exactly that. You could just return or you don't have to do anything because nothing is private, nothing is controlled by the language's syntax, so people could just access your variable directly, and you could just talk about it in documentation. Hey, look at this variable. That's fine, but even in those languages, a lot of times people end up developing convention, a lot of times starting things with underscores and stuff like that, because it's just good design to demarcate what's exposed for external use, or like your interfaces of your abstraction, versus what's internal state. That's something you want to tightly control, because you're going to have to control internal state to guarantee correctness of your algorithm, right? So that's just good design. So this way, and now Go does enforce access control. And it does that through case to the case of your variable and your function names. So any functions or methods and data fields or variables that start with a lowercase are private to the package. Anything that starts with a capital letter is exposed out to the world, but still namespaced based on your package structure we talked about, your folder and your package. You would import that into something that's external to this package. But then you can use add outside of this thing, and that's the whole intention. Whoops, I didn't mean to do that. So that's that. So that's why even though it's very easy to just expose size, we don't, because we want it to be read-only. We don't want it to be mutable, because if people external to this package accidentally, not people, but code that's external to this package, accidentally started modifying this size variable, it could be disastrous to all this logic we're about to write, right? Okay, so let's do this. Get is the next simpler one to kind of implement. And for get, what we do is we kind of start with, let's define this node to get. And this I love about Go, where you can do this type inference through this assignment operator. But we'll start at the head, right? And I'm going to be pretty aggressive here. I'm not going to be very defensive. I'm just going to assume the caller of this method knows what they're doing and leave all the error checking and yeah, basically all the error checking and defensive coding to the users of this thing. Because I'm implementing a list, and I have gotten bit with array index out of bounds exceptions quite a bit, and now I get to throw it back at them, right? Just kidding, but I'm not going to be very defensive here on purpose. Okay, so we start at the head, and then we basically, well, let's go ahead and define another thing called counter. It starts at 0. Right? And we're going to return node to get data, right? And of course counter is not used. That's fine. The other thing I want to experiment with here real quickly was I want to see if this can work. Because I think this can, but I don't know if things of different types can be signed like that. Okay, I think they can be. Awesome. So we got node to get, we got counter. Obviously, there's no while loop in Go. It's all for. So for, we'll say index, or sorry, counter is less than index, right? Node to get is going to equal node to get dot next. Awesome. And this is kind of an annoying thing about Go, where you have to cast integer types to the specific thing they're supposed to be. And that should work. Okay, awesome. So that's our get operation. And then finally we've got add, right? So before we actually implement add, I want to actually go ahead and add a method that's associated really with our node. I can actually get rid of this, this whole thing now. But yeah, let's add a method to node first. The node I want to add to, sorry, not the node, the method I want to add to node is prepend. And so why prepend? Well, you'll see how by adding this method to node, we can make the add operation we're trying to implement a constant time operation. And so let's implement prepend. So prepend is going to be basically a function on node. It's a function on node, not list, like these other guys are. And I keep making this mistake, but you really don't want to call the variable the same as the type here, because what happens is the variable ends up shadowing the type name, and then you can't use the type name in your function implementation, which is something we don't want to do at all, because we want to be able to refer to node, right? And we have prepend, and we're going to prepend a new node that we're going to create around the data that's passed in, right? So let's kind of visualize this a little bit to make it easier. So what is prepend? So let's pretend, remember the list diagrams I was drawing earlier, where we start with essentially a head node that then it has a double-ended link to the next node in the list, which then has a double link to next node in the list, and so on of whatever arbitrary size list, and then you have some tail, right? Awesome. Okay, so essentially we want to call prepend on one of these nodes. So In practice, you'll see we'll always call prepend on the head node because this is really only going to be used in the add method right now anyways. But to make the example kind of friendly for understanding, let's call prepend on n2. So if we do n2.prepend, meaning the n being passed here is going to be n2, what happens is with this data we create a new node called nnew, and it gets shoved right here in the middle of n1 and n2. What that does is it takes, first of all, it creates nn, has the data in it, and its previous and next are going to be n1 and n2, respectively. But it also changes links here and here, right? The next link here used to point to n2, now it points to nn. The previous link here used to point to n1, now it points to nn. So let's do exactly that. We're going to essentially implement what we just said there, right? What I just said there. So first we're going to create a new node. So let's just call it a new node, right? So new node, and it's going to be a reference, right? Node reference. So node, so we're going to do the fields exactly in the order that's over here. That's the Go syntax. So we have data, which conveniently I've also called data. It's not because this is data that I'm calling data, it's because this is what's getting passed in, right? And we're then saving that as data here. Next is next, and next is going to be n2. n2 is what this was called on, so that's n, right? So n. And then what is previous? Well, previous is whatever n1 is going to be, right? And n1 is right now, because we haven't changed any pointers yet, the previous of n2. So we do, which is n. So n dot previous, right? Okay, so the new node is good. You don't need to do anything else with this guy. So what do we need to do? We need to go ahead and fix the pointers for n1 and n2. So n1 we'll fix first, and that is n.previous, and then n.previous is next is what's getting fixed, right? And then we have n2, which is just n, and n's previous is getting fixed, right? And both of these guys are new node. Obviously, and then we want to return new node. And obviously, we need to capture that here. Okay, so that should work. So basically, everything I just said earlier is what we implemented here. I'll delete that because that was just for an example purpose. So now we're ready to implement add. Okay, so what is add? In add, what we're trying to do is address two cases. So essentially what we're adding is we're adding a new data node to the tail of the list, right? So we have two cases to worry about. First case is if the list is empty, which means head is nil, right? So if head is nil, meaning the list is empty, then we go ahead and basically say list.head we need to create. And obviously data is going to be data. Now it's next and previous because it's a circular list, meaning there should never be any nil references. We should always be able to get to a next or a previous. It never stops. So instead, we need to set that, but right now we can't because this is going to be a single, a list of size 1. The next and the previous are going to be itself. It's going to be a single node that's going to just keep pointing to itself. But I can't refer to something that hasn't been created yet. So we'll do that in the next line where we do previous, not depend, but previous, and this.head.next, and they both just point to themselves, or to the head itself. Okay, so that's the first case, right? Else, meaning the head is defined, meaning the list is not empty. And in that case, our implementation is very simple. We just append to head, right? Because we're pushing things to the tail anyways, so the tail in a circular list is always going to be right before the head. And we don't change the head of the list, but we do append to it. And that's how, even if the list has if the list has 0 elements, 5 elements, a billion elements, it's always going to be a very quick constant time operation to keep adding to the tail. So, and since we have all the details captured in the prepend method of creating a node and fixing the links, we just call it and be done with it. But there's one more thing to do, and that is to fix the size, because we have added a new element, so our size changes. One thing about Go has 0 values. So basically, if you declare a variable and do not initialize it, it automatically gets initialized to its 0 value. And different types have different 0 value. So basically here, a pointer's 0 value is always going to be nil. So here head, when you don't put anything in, it's going to be nil. The 0 value of any integer type or any numeric type, I think in general, is 0. For strings, I think it ends up being blank strings. For structs, it creates a struct, but then it creates 0 values for all its fields. So a value struct, which is different. So if I had a node versus a star node, so we've been dealing with pointers the whole time, but if we just created a node in the sense that this and ampersand was missing, and then we just did a node, we're actually going to do that in a second, so don't worry about it. But essentially, it creates just an empty struct where all its fields have 0 values assigned to them. Cool. So now we're actually ready to test. So we will start writing unit tests soon, but not just quite yet. We're just not ready for that yet. We're ready, but just to keep things still kind of simple. Let's just write a quick driver program. In the driver program, we just want to test 3 new operations we've created, right? The 3 public operations that we've created. So what we'll do is we'll just create an empty list and make sure its size is 0. Then we'll go ahead and add, a few elements, maybe 3 or 4 elements. Print the new size, and then we'll get each of those elements, make sure that we can retrieve things in a reliable, sane manner. And the key here is insertion order. So whatever gets inserted first gets the lower number index. And then finally, we'll try to do some error checking. We'll supply an index that is greater than size and see what happens. It should blow up, right? Because there is really no defensive code here. This just is very aggressive and assumes a lot. So we'll do all of that. Okay. So the fact that we have this person struct here is going to come in handy. We've done the hard part, so this should be fairly easy. I'll keep myself around here for a second. But before I start getting into that, let's just write the program we just talked about. So first things first, let's create the list. And this guy is just going to be a reference to, sorry, not the circular list. And we'll just do an empty struct, right? Which should give 0 values to everything here. And we should be, not here, sorry, here. And that's precisely what we want, because we want to start with 0 size in the head. Okay, and then let's go ahead and do a size. And here's where our format buddy comes in handy again. So we do a format print line. Actually, so substituting variables in the string that you want to print out is usually actually done with this printf, which should be familiar to people from most programming languages, where you kind of have your substitution characters embedded in the string itself, and then they are kind of resolved at output time. So that guy's out, and we'll say initial size should be 0, and we're going to have a %v, which means I want the value of the positional parameter that corresponds to this location. And then we'll do a \n to do a line break, and we only have one positional parameter, which is our list size. Okay, that's great. We'll go ahead and comment this guy out for now, and we'll just run it. Boom. So initial size should be 0, and it is 0. That's awesome. So let's add our first element. I like leaving white spaces as well. Okay. And so add, we just throw in some data, right? So let's go ahead and add this person, in fact. kick things off, right? Let's also add some string, and let's also add some number. All right, and then let's do this guy, right? Excuse me. So now we should have gone up to 3, right? So here, run that one more time, and now that's awesome. And obviously it's not initial size anymore, it's final size. That's a typo on my end. And then let's go ahead and start printing things out as well, right? Let's see. Let's see if this is automatically resolves. It does. Awesome. So what I was referring to earlier was this get doesn't take a normal int, it takes the uint64. So I was hoping when you just put a 0 literal in there, it knows to automatically cast it to that. And the reason I was hesitant is because we had problems, but that's because we were comparing ints and uint64, and that's something you can't do. But this you can easily do, and so that's awesome. Okay, so this should be good to go, and then we should get exactly what we're expecting. And we have a bug. That's awesome. So we did insert 3 things in here. It's just that the loop is never breaking for some reason. So let's go ahead and kill this. And let's figure out what's wrong with our get. Oh, this is what's wrong with our get, because our counter never increments. Fun little logic bugs, right? Awesome. Okay. And look at that. Just one line and it changes everything. So first should be Saharsh, and it is Saharsh. Second should be something, and it is something. Third should be 999, and it is 999. And we have successfully implemented our baby list. So now we'll be moving on to something more serious, right? To do that, I'll do some directory cleanup here because I want to start organizing my code, and then we'll build a more sophisticated list abstraction. Let's start with interfaces, because I want to really get to know Go interfaces. So we'll basically, and interfaces really are where you just kind of say, this is the contract at a very high level. No logic, no data, no state, none of that. This is just what I want my abstraction to do. It's a dummy little box to play with, right? And then you can say, okay, given this contract, here's my implementation. We'll do exactly that, because I like to develop in that way. We'll do a lot of test-driven development from here on out. So let's get into all that fun stuff. So before we start, let's kind of reorganize things a little bit here. I'm going to remove the built local file, and I'm going to create some folders here. So let's create a test folder. We'll put any driver code. We're probably not going to have as much driver code anymore. We're going to rely more on unit testing. But if we do, let's move this guy in there. Go ahead, please. Awesome. And now, fun thing is if I go into test, it actually should be building test now. Awesome. Great. Okay, so we've got our test folder separated away. We'll create a new folder here called data structures. How about that? And this is where we'll put the linked list. Basically, we'll move the circular doubly linked list implementation in there. And then we'll create our queue or stack that we build off of the circular link we built, circular doubly linked list. Wow, say that 5 times fast. In there as well. And then we'll add some more folders if it makes sense. But for now, we should be good to go with this. And yeah, let's get going. All right, so hope you enjoyed that. We're going to continue to build on everything here, and basically build a more sophisticated version of this linked list in the future episode. But for now, I'm going to stop here to keep these things kind of short and manageable. So join in the next episode where we actually build a more sophisticated version of this linked list, unit test it, figure out how to test things and go from there. Have a good one until then. Bye-bye.